Hello student, welcome to next lecture for metric spaces. In previous lecture, we have seen definition of convergent sequence, definition of Cauchy sequence and the convergent sequences in product metric space. Now we prove some theorems on Cauchy sequences. Before that, we see the definitions of convergent and Cauchy sequence. Let xt be a metric space. A sequence xn of points in X is convergent to X belongs to X if for given epsilon greater than 0 there exists a positive integer n such that d of xn x is less than epsilon for all n greater or equal capital N. Then xn is called convergent sequence and it converges to x belongs to x. Next is Cauchy sequence. Let xt be a metric space. A sequence xn in X is called Cauchy sequence. If for given epsilon positive there exists positive integer n such that distance between xn and xm is less than epsilon whenever n and m greater or equal n. Then sequence is called Cauchy sequence. Cauchy sequence means that if we have a sequence x1, x2, some of the points of the sequence are also in the form of xn, then next point will be xn plus 1 and somewhere there is a point xn and xm, xn plus 1, xn plus 1, xn plus 2, xm and so on. Then if for given epsilon positive there exists n belongs to capital natural numbers, that means for fixed value of xn, after this term of the sequence the distance between two terms of the sequence xn and xm is negligible. That will be less than epsilon whenever epsilon is the smallest positive number. That means after this term xn of the sequence, the distance between 2 points of the sequence is less than 0. That 2 points will be same after sum. Hence, this is what the meaning of Cauchy sequence. Now we prove one theorem. Theorem is let xn be a convergent sequence in a metric space xd such that xn converges to x as n tends to infinity if xnk is any subsequence of sequence xn, then xnk converges to x. What is meant by subsequence? If we have a sequence of points in the metric space xt, then choose the points of the sequence which forms again a sequence. From this point, from this set, if we choose some points that will form again a sequence, then that is considered as subsequence of this sequence. This X can be a convergent sequence in a metric space Xt such that Xn converges to X. What is the definition of convergent sequence? Xd is a metric space, Xn converges to X if for given epsilon positive there exists a positive integer n such that d of xn x less than epsilon for all n greater or equal capital N. This is the definition of convergent sequence, since it is given that sequence xn is convergent. Now what we have to prove? We have to prove if xnk is subsequence of xn, then xnk also converges to the same limit to which sequence xn converging. Subsequence converges to the limit at which original sequence convergent. We know that every convergent sequence is Cauchy sequence in a metric space. Hence, the given sequence is Cauchy sequence. Therefore, by definition of Cauchy sequence, for given epsilon positive, there exists n belongs to set of natural number such that d of xn less than epsilon for all n also m greater or equal capital N. In above state, we have considered xn is a convergent sequence. For given epsilon positive, there exists a positive integer n such that d of xnx less than, suppose this is epsilon by 2. Because we consider any radius, if epsilon is greater than 0, then epsilon by 2 can be also considered as radius. Also, the sequence is Cauchy sequence because the convergent sequence is Cauchy sequence. In last lecture, we have proved that result. For given epsilon positive, the definition of Cauchy sequence is there exists natural number such that d of xn less than epsilon for all m n greater or equal capital N. We take this as epsilon upon 2 for all m n greater or equal capital N. If we choose m is equal to nk, okay, and nk greater or equal capital N. This is what Cauchy sequence. If n and nk are greater than n, then d of xm and xnk less than epsilon by 2. This implies d of xn k and xn is less than epsilon by 2 whenever n and nk greater or equal capital N. Hence, if we consider d of xnk and x, this is less than or equal to d of xnk xn plus d of xn x, where by triangle inequality this value is less than epsilon by 2, this is strictly less than epsilon upon 2, plus being convergent sequence d of xnx less than epsilon by 2, which is equal to epsilon. So what we proved? D of xnk x less than epsilon for all nk greater equal capital M. Hence, the sequence is convergent sequence. This implies which sequence is convergent sequence? Sequence xnk convergent, and it converges to x. We will see the next theorem. Converse of this theorem is not true. If the sequence x and k converges to x in the metric space X, but the original sequence for which we are considering its subsequence need not be convergent. For example, let xn is a sequence minus 1 raised to n in Ru. Then consider subsequence xnk of this sequence xn as 1, 1, 1 and so on. These terms of the sequence are minus 1, 1, minus 1, 1 and so on. We can consider its subsequence as xnk is equal to 1, 1, 1, 1 and 1. So xnk is a constant sequence, hence it converges to its constant limit, that is 1. xnk converges to 1. That is subsequence xnk of sequence xn converges to 1, and 1 belongs to R, but the original sequence xn is not convergent. Since if xn will be convergent, then limit n tends to infinity xn exists. But for this sequence, limits are not unique. It's one of the subsequence. Suppose that is minus 1, minus 1, minus 1, minus 1, that converges to minus 1, and this subsequence converging to 1. Hence, limit of the sequence is not unique, therefore this is not a convergent sequence. Now we go to the next theorem. Xn be a Cauchy sequence in a metric space xt, then xn is convergent if and only it has a convergent subsequence. Proof. What is given? Let xn be a Cauchy sequence in a metric space. This is a common statement to both the statements. xn is a Cauchy sequence in a metric space xt. Therefore, by definition of Cauchy sequence, for given epsilon positive, there exists a natural number n such that d of xn is less than epsilon upon 2 for all m n greater equal capital M. Instead of m, if we consider x and k, if m equal to nk, then d of xnk xn is less than epsilon upon 2 whenever nk n greater equal capital N. Consider this as equation number first. Now assume any one of the statement of this theorem. If xn is convergent sequence, then we have to prove it has a convergent subsequence. What is the definition of convergent sequence? For given epsilon positive, there exists a natural number n. Here we have a Cauchy sequence as well as a convergent sequence. Hence we use this positive integer notation as n1. Also here we use n1. And being convergent sequence, for given epsilon positive, there exists n2 belongs to set of natural number such that d of xn x is less than epsilon upon 2 whenever n greater equal n2 and x belongs to metric space xt. Then xn sequence converging to x. Okay, consider this as equation number 2. What we want to prove? We want to prove xn has a convergent subsequence. Means if we consider xnk as a subsequence of xn, then consider d of xnk x by triangle inequality. This is less than or equal to d of xnk xn plus d of xn x. This is strictly less than epsilon upon 2 plus epsilon upon 2 whenever nk n greater than or equal to n. This is the maximum of n1 and n2. Hence d of xnk x is less than epsilon for all nk n greater equal capital N, which is a positive integer. Therefore, what this implies? Sequence xnk converges to x. Hence, if xn is convergent, then it has a convergent subsequence, and that subsequence converging to the same limit to which this sequence xn is converging. Conversely, suppose xnk is convergent subsequence of xn, sequence xn, then by above theorem sequence xnk converges to x, where sequence xn also converging to x. By above theorem, what is the above theorem? Just now we have proved that theorem xn is a convergent sequence in a metric space. If xnk is a subsequence, then xnk converges to the same limit to which sequence xn is converges. Here we have xn as a convergent subsequence. Therefore, if xn is convergent, xnk is convergent subsequence of xn, then by above theorem xnk converges to x, to which the original sequence converges to x. It is also given that xn is a Cauchy sequence. Hence, the distance between any two points of the sequence xm and xn will be less than epsilon whenever mn greater equal capital N. Right? Therefore, if subsequence xn converging to x, then xn should converges to x. xn converges to x. Thank you.